Now let us look into further concepts in the centrifugal pump. Now let us see the minimum starting speed, which is also denoted as N minimum. So this is the minimum starting speed before which, so if you don't achieve this speed, then the pump will not be providing any output, or there won't be any outflow from the pump if the speed is less than the minimum starting speed. So now to find out the minimum starting speed, first let us understand the centrifugal head. So the centrifugal head achieved by the pump is the amount of energy imparted into the fluid, and that is given by U2 square minus U1 square divided by 2G. If the centrifugal head is less than the manometric head, then the water or the liquid will not have sufficient energy to reach the delivery height, okay, to reach the delivery side of the pump. So for that purpose, what we have to do is we need to maintain a speed greater than the minimum starting speed, so that we have a proper output from the pump. So here the flow starts when the centrifugal head is greater than or equal to the manometric head. And for minimum condition, so the minimum condition for the flow to start is U2 square minus U1 square divided by 2G, which is the centrifugal head, should be equal to the manometric head. If we talk in terms of Euler's head, then that is given by manometric efficiency into Euler's head, because if you remember, manometric head or manometric efficiency is the ratio of HM, that is manometric head, divided by the Euler's head. Euler's head is the theoretical head. If you remove the losses, then we will get the manometric head. So U2 square minus U1 square divided by 2G, which is the centrifugal head, that should be at least equal to the manometric head, which is the actual head developed by the pump, which is equal to manometric efficiency into Euler's head. And if you substitute the value of U2 as pi d2 n divided by 60 and U1 square as pi d1 n divided by 60, and if we rearrange the equation, then we get the minimum starting speed as 60 by pi whole squared multiplied by 2G into eta m, that is manometric efficiency into Euler's head, because we will be calculating Euler's head in our theoretical calculations, divided by d2 square minus d1 square whole root. So this gives us the minimum starting speed of a pump, which means to say that the flow will start only if the pump reaches this speed. If the speed of the pump is less than the minimum starting speed, then there will be no output or outflow from the pump. So for the flow to start, we need to achieve this speed. After this only we will be able to get the output from the pump. Now let us move on to the next concept, that is the maximum section lift and net positive section head. If we are talking about liquids, they will be stored in a sump, and the sump will be exposed to atmosphere. So the maximum suction head that can be achieved will be equal to the atmospheric pressure at that location. Let us take the atmospheric head as HA, and this is the maximum suction head which can be produced by any pump, but that is only applicable in an ideal case. In real cases, there are so many factors which leads to losses. The first one is we have the friction head in suction pipe. So there will be fluid friction, and there will be friction between the inner surface of the suction pipe and the fluid. So because of those two reasons, there will be loss of some head. So that I will call it as HFS, that is head loss due to friction in the suction side. Then we have the dynamic head in the suction pump. The liquid will be flowing with a certain velocity. I call it as Vs. Vs stands for velocity in the suction pipe, and Vs square by 2G represents the dynamic head in the suction pipe. Again, this cannot be recovered. So these two are the losses. So now if I want to find out the maximum section lift, so the maximum section lift can be written as MSL, which is equal to HA, that is the maximum head which can be developed by a pump, minus HFS, that is the frictional loss due to the fluid friction as well as the friction between the surface and the tube surface and the fluid, and then the dynamic loss, that is V square divided by 2G. So this is the maximum section lift that can be achieved by a pump, which means to say that from the sump level, from the sump free surface level, we can keep the pump at this maximum height. And if you have to consider the cavitation or the formation of vapor bubbles inside the suction pipe, then that also has to be subtracted. So if vapor pressure head is denoted as HP, then the maximum section lift, so the maximum section lift will be equal to HA, that is the maximum for an ideal case, minus the losses, that is HFS, minus VS square divided by 2G minus HV, where HP represents the vapor pressure. So if you don't consider the vapor pressure, then what happens is, if there is a slight increase in the head above the maximum section head, that leads to the formation of bubbles, vapor bubbles inside the suction pipe, and that may lead to cavitation and the damage for the suction pipe as well as the pump. So we need to consider the vapor pressure head while calculating the maximum section lift. So, and that is the position where, that is the maximum height where you can keep the pump from the sump. So if the pump is greater than that, then there will be cavitation as well as the pump will not be able to suck the liquid from the sump. Now to guarantee that there is sufficient head available, so no cavitation occurs and no vapor occurs, no formation of vapor occurs in the pump. So what we can do is, we have a concept called net positive section head. So that guarantees us that if the value is higher, if it is positive and higher, then that guarantees that there won't be any formation of vapor bubbles in the suction pipe. So that guarantees the safe working of the pump. So for that, let us assume suction head of the pump is HS, that is the actual head which we need to develop. So that is where we have kept the pump. So that is the height from the sump where we have kept the pump. For the safe working, as I said, the maximum section lift should be greater than HS, which means to say that if the maximum section head is maybe 10 meters, then if we have to develop a height, or the height we are keeping this pump at a height of 9 meters from the sump, then for safe working the maximum section lift of that pump should be greater than 9 meters. So here for safe working, MSL should be greater than the section head, and the net positive section head, which is written as NPSH, is the difference of MSL and HS. So NPSH is equal to MSL minus HS, and if the value of NPSH, that is net positive section head, is greater, then it guarantees that the pump will be working under, always the pump will be working under safe conditions. That is the use or the concept of net positive section head. So we need to maintain a net positive section head, that is the difference between MSL and HS, and that ensures us that the pump is working under safe conditions and no vapor bubbles will be formed in the suction side, and that is the way majority of cavitation occurs, because that is the region of low pressure. So there we need to maintain net positive section head so that there will be no formation of vapors as well as cavitation. Now let us solve few problems. First one, a centrifugal pump delivers 1800 liters per minute against a total head of 20 meters. Its speed is 1450 rpm. Inner and outer diameters of the impeller are 120 mm and 240 mm respectively, and the diameter of suction and delivery pipe are both 100 mm. Determine the blade angles beta 1 and beta 2. if the water enters radially. Also, find the power required to drive the pump. Here, let us list out the data given in the problem. The first data given in the problem is the discharge is 1800 liters per minute. I have converted that to meter cube per second. So, to do that, I have to divide this by 1060, 1000 multiplied by 60. So, then we get 0.03 meter cube per second. Against a head of 20 meters, so h is equal to 20 meters and its speed is 1450 rpm. Then the inner diameter is given as 120 millimeter, which is 0.12 meters. Outer diameter is given as 240 millimeter, which is 0.24 meters. Then the suction side pipe and the delivery side pipe both are having a diameter of 100 millimeter, which is 0.1. Then we need to find out beta 1 and beta 2, the blade angles, if water enters radially. So this sentence is very important for us to construct the inlet velocity triangle. So since the water is radially entering, the angle at which the fluid is entering will be equal to 90 degree. That is, alpha 1 will be equal to 90 degree. So the inlet velocity triangle will be a right angle triangle. Then we need to find out the power required to drive the pump. Okay, now we have listed all the data. Now let us start with the tangential velocities u1 and u2. So u1 is given by pi di n divided by 60, which is equal to pi into di is 0.12 multiplied by 1450 divided by 60. So we get u1 as 9.11 meter per second. So u2, it is pi into outer diameter into n divided by 60, which is equal to pi into 0.24 into 1450 divided by 60, and u2 is given as it's 18.24 millimeter per second. Now we have the tangential velocities at the inlet and outlet of the rotor. Now we need to find out. So now let us draw the inlet and outlet velocity triangles here. So since I know water enters radially, inlet velocity triangle will be a right angle triangle. So here we have our inlet and outlet velocity triangle. Since I know that water enters radially, so the angle alpha 1 will be equal to 90 degree. This is beta 1. So we have an right angle triangle at the inlet. So this is the base is u1 and this vertical line is v1, which is also equal to vf1, and then we have vr1. So the angle made by vr1 is beta 1, and we have the outlet velocity triangle where we have u2. So u2 is towards right, both u1 and u2 will be in the same direction. Then we have v2 here. If we join the two ends of u2 and v2, we get vr2, and I'll resolve v2 into vertical and horizontal components. So the vertical component is vf2 and the horizontal component is vu2. Here vu2 is towards right. Okay, now let us find out the angles beta 1 and beta 2. For that, first I'll take the inlet velocity triangle. If I take the inlet velocity triangle, I know that I know u1. If I am able to find out vf1 or vf, because here it's a steady flow device, so vf1 and vf2 will be same because the diameter at the section and the diameter of the pipe of section and delivery pipes are same here. So vf1 and vf2 will be same. So if I am able to find out the flow velocity vf, then I will be able to find out beta 1. So now let us try to find out vf. So we know u1 and u2. and if you know the width of the blade, then you will be able to find out Vf1 and Vf2. But since we don't know the width and we know the discharge, I will use the suction or the delivery pipe diameter to find out the flow velocity. Since both are same at suction as well as delivery pipe, the flow velocity will be same. So I can write Q will be equal to Vf into area of flow AF, or I can write Vf is equal to Q divided by AF, which is equal to 0.03 divided by flow area is pi d square by 4, because that is the cross sectional area of the pipe. So it is pi into 0.1 square pi d square by 4, pi into 0.1 square divided by 4, and if you simplify this, we get the flow velocity as 2.65 meter per second. The flow velocity is 2.65 meter per second. Now I know the flow velocity, so I can find out beta 1 and beta 2. Since I know the flow velocity now, I can find out beta 1 and then we will go to beta 2. So from the inlet velocity triangle, tan beta 1 will be equal to opposite divided by adjacent side. The opposite is Vf divided by adjacent is U1. So which implies that beta 1 will be equal to tan inverse of Vf is 2.65 divided by U1 is 9.11. So I will get beta 1 is equal to around 16.2 degree. Now to find out beta 2, again I need Vf and I need this length. So this I will call it as just x. I need x as well as I need Vf2. Since I know Vf, now I need to find out x. And from the outlet velocity triangle, we can say that x will be equal to u2 minus Vu2. We already know the value of u2. U2 is 18.24. Now we need to find out the value of Vu2. So for that, what I will do is I will make use of the head. Okay. So here they have not given any losses. They have not talked about any losses. So whatever the head given, h, which will be the monometric head, I will also consider that to be equal to Euler's head. And Euler's head is given by u2 Vu2, because Vu1 is 0. Since V1 is a vertical line, the horizontal component of V1 will be 0. So the head here is given by u2 Vu2 divided by g, u2 Vu2 divided by g, because Euler's head, from the Euler's equation we say that energy transfer will be equal to g into h, where g into he, where he will be the Euler head. So now to get Vu2, I can rearrange this as Vu2 will be equal to he into g divided by u2, which is equal to he is 20 meters into g is 9.81 divided by u2 is 18.24. So when we calculate Vu2, we get the value of Vu2 as 10.77 meter per second. Now I know the value of Vu2. Now I can find out the value of x and I can find out beta 2. So from the outlet velocity triangle, I can write tan beta 2 will be equal to opposite by adjacent side opposite is Vf divided by adjacent side. Instead of writing x, I will write it as u2 minus Vu2. So I can write beta 2 will be equal to tan inverse of Vf. Vf is 2.65 divided by u2. Here u2 is 18.24 minus Vu2 is 10.77. So I get beta 2 as 19.58 degrees. So this is the value of beta 2, and beta 1 is 16.2 degrees. Now we need to find out the power. So the power, the hydraulic power is given by rho q g into He divided by 1000 kilowatts. I am dividing this by 1000 to get the answer in kilowatt. Now I know rho, it's water. So rho is 1000 kg per meter cube. Q discharge is given, G is 9.81 and He is also given. Now I will be able to find out the power. So I can write power will be equal to 1000 multiplied by 0.03 multiplied by 9.81 multiplied by 20 divided by 1000. So if you simplify this, then we get power as 5.89 kilowatts. So this is the power developed by the centrifugal pump. A centrifugal pump of 100 mm by 100 mm size has a suction lift of 2.5 meters and a delivery lift of 28 meters. The suction pipe is 3.5 meter long and the delivery pipe is 22 meter long. The friction factor is 0.025. Water enters radially and the outlet vane angle is 26 degree. Calculate the discharge and the input required if the hydraulic efficiency is 0.75 and the mechanical efficiency is 0.88. The impeller is 30 centimeter diameter and 2 centimeter wide with a speed of 1400 rpm. Now let us list out the data given in the problem. In this problem they have given that the size of the pump is 100 mm by 100 mm, which means to say that the suction pipe and the delivery pipe has a diameter of 100 mm. So the ds and dd, that is the diameter of the suction pipe and the diameter of the delivery pipe is 100 mm, which is equal to 0.1 meter. Then the suction lift is 2.5 meters and the delivery lift is 28 meters. And the length of the suction pipe is 3.5 meters and the length of the delivery pipe is 22 meters. And he says that the friction factor is 0.025 meters and water enters radially, which means to say that alpha 1 is equal to 90 degree, and if you write inlet velocity triangle, it will be a right angled triangle. Then the outlet vane angle, that is beta 2, is 26 degree. For this we need to find out the discharge and the power input required for the shaft, and for that purpose he has given different efficiencies, that is hydraulic efficiency is 0.75, which is also equal to monometric efficiency in case of a centrifugal pump. So for centrifugal pumps the monometric efficiency and hydraulic efficiency are same, and he has given the mechanical efficiency as 0.88. He has given the vane diameter at the outlet, so I will write it as d naught is 30 centimeter, that is 0.3 meter, and the width of the blade at the outlet, you can call it as b naught, which is equal to 2 centimeter or 0.02 meters, and the speed he has given it as 1400 rpm. So now we need to find out the discharge and the power input. First we need to find out the monometric head, and we know that for a pump the monometric head is given by, since here he has given the suction head, delivery head and the friction factor. So we need to consider all those things, and this is given by Hs plus Hd plus Hfs plus Hds plus Vd square divided by 2g. Here Hs is the head suction lift, Hd is the delivery lift, Hfs is the friction losses that occurs in the suction pipe, and Hds is the friction losses that occurs in the delivery pipe, and Vd square by 2g is the dynamic head at the delivery pipe, which we are going to lose when the water enters the overhead tank or when the liquid enters the overhead tank. We know the value of Hs, Hd. Now we need to find out Hfs, Hds and Vd square by 2g. So let us write Hfs, which is equal to, here he has given the friction factor. For that purpose I will write it as Fls Vs square divided by 2g into ds. But we don't know the velocity in the suction pipe, so I will write that in terms of discharge. So this can be written as Fls divided by 2g into ds multiplied by, it is velocity can be written as, so I will just write it here, Q is equal to A into V, or V can be written as Q divided by A. In this case area is pi d square divided by 4, so I will write it as 4Q divided by pi d square, and here we have square for that, so it becomes 16Q square divided by pi square into, it is Vs, so it is ds to the power of 4. Okay, that is the head, that is the friction loss in the suction pipe. Now I will write Hds, which is equal to Fld Vd square divided by 2g dd, that is the diameter of the delivery pipe, which is equal to Fld divided by 2g into dd multiplied by, similar to this, it becomes 16Q square divided by pi square into dd to the power of 4. So I have Hfs and Hds, sorry, this should be Hfd, friction loss in the delivery pipe. Then we need Vd square. I will use the same concept here. Vd is given by Vd square is given by 16Q square divided by pi square into dd to the power of 4. I will divide this term by 2g to get the dynamic head at the delivery pipe. Now I will write Hm, so this will be equal to Hs, Hs is 2.5, I will substitute the values directly, plus Hd is 28, plus here F is given 0.025 and L is given and the diameters are given. So I will write 0.025 into Ls is 3.5 divided by 2 into 9.81 into ds is 0.1. Now Hfd also contains the same term here, ds and dd are equal, so ds and dd are equal, and here also we have Vd square which has the same term, so I will group them together, I will write it as plus. Now I will take up this, again F is 0.025 into Ld is 22 divided by 2 into 9.81 into dd is 0.1, plus here I have 1 over 2 into 9.81, everything multiplied with this term, which is 16 q square divided by pi square into dd and ds are same, 0.1 whole to the power of 4. Now if we simplify this, we get Hm will be equal to 30.5 plus 6094 times of q squared. So when we simplify this, we get an equation Hm is equal to 30.5 plus 6094 times of q squared, and I'll call this as equation A. And I know that the Euler's head He is given by U2 Vu2 divided by G. Or in other terms, if I know Vu2 and U2, I'll be able to find out He, and the monometric head is given here, which is the ratio of Hm divided by He. So I can easily find out Q. So for that, I'll draw the outlet velocity triangle here. So if I draw the outlet velocity triangle, this entire length is U2, this is Vu2, this is V2, and this is Vr2, and this is Vf, and this angle is beta 2, this is alpha 2. Now in the problem they have given beta 2 as 26 degree. I know this, it's 26 degree. I need to find out Vf. So if I know Vf, since I know beta 2, I'll be able to find out Vu2 if I calculate U2. So first let us calculate U2. So U2 is given by pi d2 or d naught n divided by 60. D naught is given as 3.3 meters and n is given as 1400. So it is equal to pi into 0.3 into 1400 divided by 60. So U2 will be equal to 21.99 meter per second. Now I know U2. Now from the outlet velocity triangle, so I need Vu2, so I can write Vu2 as U2 minus, I'll call this as X. So this since I know beta 2, I use tan here or cot beta 2. Cot is adjacent by opposite. So cot beta 2 will be equal to adjacent, which is X, divided by opposite, which is Vf. So I can write X will be equal to Vf into cot beta 2. So it is my U2 minus Vf into cot beta 2. I don't know Vf, so I use this concept to find out Vf, and here Vu2 will be equal to 21.99 minus, so in place of Vf I'll write it as Q divided by pi into d naught into b naught. So d naught into b naught is the flow area at the outlet, and multiplied by cot 26. So if you simplify this, you get Vu2 as 21.99 minus 108.77 times of Q. Now I'll substitute that here to find out the Euler's head. So He will be equal to U2. U2 is 21.99 multiplied by Vu2 is 21.99 minus 108.77 Q divided by 9.81. So when we simplify this, He, we get it as 49.29 minus 243.8 times of Q. I call this as equation B. Now I know the monometric head or the monometric efficiency or the hydraulic efficiency. So monometric efficiency, which is equal to hydraulic efficiency, which is Hm divided by He, or I can write Hm is equal to hydraulic efficiency into He, which is 0.75 times of He. Now I will substitute Hm and He by using equation A and B, and I can write Hm is here 30.5 plus 6094 times of Q to the Q square. This will be equal to 0.75 times of He is 49.29 minus 243.8 times of Q. So now if you simplify this, then Q is the unknown and we get an equation Q square would be equal Q square plus 0.03 times of Q minus 0.00106 will be equal to 0. And Pythagoras formula to find out the roots of this equation, and that will be the value for Q. So Q can be written as minus B 0.03 plus or minus root of B square, which is 0.03 square, minus 4A into B. So here minus 4AC, C is minus 0.00106. So I'll write it as plus 4 into 0.00106, everything divided by 2A, which is 2. So from this we get Q as 0.021 meter cube per second. So now we have the discharge. I'll substitute the value of discharge in He and Hm equation, that is equation A and B. Then I'll get Hm will be equal to 33.19 meters and He will be equal to 44.25 meters. Now we need the power. So power can be calculated. The power input for the water will be equal to rho Q G He. Now we know He and we will get the power as rho is 1000 into Q is 0.021 into 9.81 into 44.25. So the power developed for the water, I'll just call it as P, will be equal to 9.1 kilowatts. The mechanical efficiency eta mech will be equal to power developed by the water divided by power input to the shaft. So I'll write power input to the shaft as power IP input to the shaft will be equal to power developed divided by mechanical efficiency. So that will be equal to 9.1 into 10 to the power of 3 divided by mechanical efficiency 0.88. So we get the input power required as 10.34 kilowatts. So this is the power input required and this is the discharge developed in this